Welcome to this talk on how one can use generative adversarial networks to generate 2D aerial maps for role-playing games. Town maps have several functions in role-playing games. Firstly, maps significantly increase the immersion of the player in the geography, history, and character of the game world. While immersion does not appeal to all players, a second function of maps, which even the most casual of gamers rely on, is for navigation. In order to address this need for maps in tabletop or 2D digital role-playing games, several artists produce hand-drawn maps for game creators and game masters to use, or even just for the joy of sharing concepts of game worlds imagined by the artist. Maps are also of importance in other forms of art where narrative takes place, such as books. Several communities of such artists have formed, such as Cartographers Guild and Cartographic Guild on DeviantArt, which demonstrates that map-making has a third function in contributing towards the artistic and aesthetic element of the game or art form they are included in. This research is aimed for 2D maps and takes tabletop RPGs as a context, although the concepts which will be covered can easily be adapted to any digital artifact as long as it is in 2 dimensions. Content creators who are not skilled in drawing rely on tools to assist them in representing their concepts visually. For the purposes of this talk, we will distinguish between two categories of tools. The first are those which serve to draw maps but have no participation in its design, which is undertaken by the user. The second category consists of tools which design the map by themselves, placing elements according to some convincing real-world layout. Some tools belong to both of these categories, first generating the design and then texturing it. This talk will focus on drawing maps that are designed by the user. Work is underway to use AI to design maps itself, but this will not be discussed here. For this reason, only the first category of tools are relevant for comparison in this case. Current tools for helping users to draw maps are unfortunately limited by the number of different textures or sprites provided by the system. This results in repetition, which is particularly evident when the tool does not provide enough variance for a reasonable map size. This presents one limitation in currently available tool, in that this repetition detracts from the believability and appeal of the resulting map. In addition, the dependence on a large library of sprites requires a skilled artist, which incurs a cost for the company producing the tool and increases the price at which these services are offered to user. In order to address these limitations in this talk, a generative approach is presented to replace sprite-based map drawing. Generative adversarial networks, or GANs, are a category of generative machine learning techniques consisting of two components with opposing objectives, competing with each other in a balanced setting. The generator aims to learn the distribution of the given dataset and improve its ability to produce new samples that believably belong to the target domain. The second component, the discriminator, aims to learn to distinguish between real examples from the dataset and the fake output created by the generator. The extent of success of one component provides feedback to the other for improvement in what amounts to a Nash equilibrium that learns structured information about the target domain, as opposed to mere colored differences. In images, GANs have been used to create realistic examples from various domains, most notably Karas's work on generation of faces. GANs in image applications can be empowered with more information, other than that present in the dataset itself, with methods such as conditioning and multimodal operation. In the case of conditioning, a segmentation map, which is essentially a per-pixel classification of the original image, is also provided to the network. This allows a single GAN to generate different categories of output in different parts of an image. These variants are known as Conditional Generative Adversarial Networks, or CGANs, and have been used to generate different digits, different types of apparel, and most notably in image-to-image translation between various domains, as described by Isola and later adapted to several other applications. In these cases, during training, both the image and the segmentation map are provided to the model. On the other hand, during inference, only the segmentation map is provided to the network, and the network in turn outputs a feasible image that matches the layout present in the input. This research aims to apply conditional generative adversarial networks to perform image-to-image translation between color-coded map designs and fully textured maps. Every map feature that needs to be represented by the final model corresponds to a particular RGB color. The number of distinct features, such as grass, houses, water, trees, and so on, that the model needs to represent has to be selected carefully. This work experimented with sets of between 10 to 34 distinct features in different trials. Once a decision was made on which features to represent, a handful of high-resolution town maps were segmented by hand into the various features. This work differs from traditional image-to-image translation because it aims to support between inverted commas infinite resolution. For this reason, the maps are fed into the network as overlapping tiles instead of whole maps. The output of the network will eventually also consist of separate tiles, which will need to be patched later. The tile size chosen is 512 by 512. Data augmentation is applied to the dataset. The context for this research allows for a wide range of data augmentation techniques, including scale, rotation, jittering, and flipping, given that none of these operations influence the semantics of the content in the case of aerial town maps. By means of tiling and data augmentation, one can get reasonable results with as little as 10 high-resolution maps. This is important given that good quality town maps are usually very detailed and it is very time-consuming to segment all features by hand. The model used for this work is adapted from the TensorFlow Pix-to-Pix implementation for facades. Only the changes from this implementation will be mentioned here. Two discriminators with different depths were experimented with to catch structural detail at various scales by virtue of the different sized receptive fields. This is in line with results shown in recent advancements in the field, although it is generally achieved by scaling down the input image instead of increasing the depth of the discriminators. A 2-layer discriminator and a 5-layer discriminator seem to work well for this application. The generator receives the mean of the two discriminators as feedback for its own improvement, trying to fit its model as best as possible to satisfy both levels of detail. The generator is one level deeper to account for the increase in size to 512 by 512 from the original implementation. Batch sizes of 5 to 20 samples work best, typically 10 samples. The system was trained for 400 epochs with a dataset of around 2000 samples, split between training and test set in a 70 to 30 ratio. Further training does not seem to produce significant improvements. It was found that with such a diverse tile dataset, where only the most common of features, such as grass, appears in each tile, the usual 80 to 20 ratio is not sufficient to assure a representative sample of many features in the test set to be able to direct training properly. Training produces a model that generates fully textured tiles, but when these are derived from a single large image, they are not guaranteed to have edges that match adjacent tiles, given that the network has no information about the surroundings of each tile to know how to draw objects at the edges. This often leads to the appearance of significant seams when patching the tiles to reconstitute the whole map at the resolution of the segmentation map given as its input. An algorithm therefore has to be brought forward to be able to provide a seamless result. While a couple of alternatives are being experimented, the most simple algorithm involves rendering the same image multiple times using different amount of tiles. The final image is then derived from the colors of the respective pixels in each layer, based on the distance from the center of their tile in the separate renders. In order to ensure that the edges do not occur at the same location across different renders, the number of tiles per dimension has to be a prime number. Examples of the output from the system described above will now be demonstrated. This 104 by 104 segmentation map was manually designed using a tool developed specifically for this research. The image was processed using 4 layers of tiles. The result shows that 4 layers are sufficient to blend seams in the majority of circumstances. One can observe that some of the potential detail is lost because of the averaging across layers. Since the blending algorithm produces more tiles, hence a larger output, this method allows the system to produce images that are larger in resolution than the image given as input, with little or no loss in quality. This is a 4K output generated from a 1K segmentation map. Before zooming in on the detail, one should point out a failure mode of the system described above. Whenever a tile is constituted entirely of a single label, as in this case all water, the system is not able to generate a texture that is consistent with its surroundings. Notice that this problem is not visible on the island, where there is more detail and variety. Experimentation seems to suggest that this issue is not related to the tiling algorithm, but is an inability of the network to predict an accurate color for the label in the absence of surrounding information. For example, water close to the shore is generally drawn a lighter color and may have more detail representing waves breaking against the rock or shoreline. For this reason, users are recommended to use maps that have enough detail such that there are no large expanses of the same feature. In any case, closer visual inspection on this 4K image suggests that the generative approach can compensate for scaling artifacts normally observed with raster images. Drastic scaling by a factor of 4 or more generally causes blocking along the edges of objects. This is a shortcoming of scaling up and not of the generation itself, and can easily be overcome by blurring the image after scaling and before tiling. Gaussian blurring often reduces contrast and results in artifacts caused by the introduction of new color gradients that the network is not trained on. Median blurring, on the other hand, as shown here, is generally more adequate, although it may lead to slight rounding of corners. The system was also tested on segmentation maps designed procedurally, using some of the tools described in the introduction. By changing the color schemes of these tools to match the one recognized by the generative adversarial network used in the system. Shown here are some output from 2048 by 2048 maps designed using medieval role-playing city generator. This software does not use the entire potential of the network in representing different features, but nevertheless demonstrates that procedural techniques can be integrated with the system to speed up the design of the maps as well as its coloring. This study is still in the process of collecting analytical results, such as user opinion scores and segmentation results, which will be reported in related publications. Meanwhile, should you wish to experiment with the system for yourselves, you are invited to use the tool produced as part of this research, which you can find on the link shown here. Earlier, it was mentioned that experiments were carried out on different sets of features. It was found that while using more features increases specificity, it complicates training, especially if some features, small details such as statues or fountains for example, appear much less frequently in the dataset of hand-drawn images. These features tend to be drowned by more frequently encountered ones and are not learned well by the network. The technique for patching provides a reasonable solution to producing high-resolution output, but is not without side effects. First of all, it is performance-intensive, as the same image has to be rendered more than once. Secondly, using too many layers leads to blurring of the image and loss of fine details, given that the algorithm depends on averaging colors between different layers. This talk has presented a method for generating output that is unbound by the native resolution of the generative network, allowing its output to reach arbitrary resolutions. Further work along these lines will include overcoming the performance issues of the patching algorithm described here, using other promising artificial intelligence techniques such as painting to fill in the borders instead of blending. It would also be helpful to adapt an artificial intelligence technique to generate new map designs apart from texturing existing ones. Eliminating the time-consuming map design step would automate the entire process and reduce the time needed to produce a map for the scenarios presented in this work. Thanks for your attention.